Hello there, welcome back to our discussion on the voltage and current references. And in our previous talk, we discussed about how to generate a current reference which has independence from the temperature variation. So we generated a current with the positive temperature coefficient, and we generated current with the negative temperature coefficient, and we added them together to generate a current which was independent of temperature variations on the first order. Now, in this talk, we are discussing about the voltage reference, and in particular, the band gap voltage reference. So as you can see that the first question that arises, what is a band gap reference and why do we need it? So band gap reference is a voltage source which has output voltage as a reference equal to 1.12 volts. And the name comes from the fact that the silicon has a band gap of 1.12 electron volt. And out of the silicon, we use the transistors, we make the transistors, and from those transistors, we build a circuit to generate the V reference that is equal to 1.12 volt. It is said that if you manage to generate the 1.2 volt reference, which is corresponding to the silicon band gap, it will ideally have TCF is equal to 0. That is temperature coefficient equal to 0. So now in this talk, we would see how that is possible. So the first question is, why do you need a band gap reference? We can use simple Zener diode as we discussed in our previous modules, but the using Zener diodes and some other options has some issues. The first is we want a reference less than 5 volt. So as in this case, we are talking about generating a 1.12 volt reference or even smaller. So Zener diode in particular, regular references using Zener is not possible at a first instance to generate the references below 5 volts, because the breakdown voltage of Zeners possibly not easier to find to have that kind of breakdown voltages. Okay, band gap reference is also we need because it is simple to implement, as we are going to see in this session. We don't have a Zener diode. It means we don't have a noise which are inherent with the Zener diodes. So in the band gap, we'll not use the Zener diode. So we get rid of noise associated with the Zener diode. And then as we know that as the technology is evolving, the supply voltages for the circuits are scaling down, smaller and smaller supply voltages up to 1 volt and even lesser are being used to bias the circuits. And in that category, your band gap references up to 1.12 or even smaller can be used to cooperate with that scaling of the supply voltages. Okay, so this is the most important reason we need the band gap references. So where do you use the band gap references? They are available as a standard reference ICs. So you just search Google or go to the vendor and ask for the reference ICs and see the data sheet on that number of the ICs, the part number. And if it is band gap reference, you'll see that. And of course, we need the data converter ICs such as ADCs and DAC. And there you need a reference to provide a reference to the DACs, the ADC and digital to analog converters. So reference are also a part of those ICs. Okay. Now let us step by step understand how we start the design process and understand the fundamental principle behind designing a band gap reference. And we'll also in the same session, I will design that using the circuit simulator and simulate it, the performance. We'll run some analysis and we'll see voltages, currents, and the most important, the temperature behavior. So what we know, we need the BJT as shown right here. As you can see, this is an NPN transistor with the current indicated and with the directions. The voltage is also indicated, VB and VC, and we want to generate the reference voltage first, which will have the temperature behavior associated with also VBE. So in the previous one, in the previous modules, we saw that, okay, we use the resistor, for example, and then we have this V plus, and then we use this diode connected transistor, for example, right here. Right here. So this transistor will always be operated in the linear mode or active mode. And then we just mirror this transistor's current into the another transistor, let's say Q2. So we've seen that, and that's how we generate this I out, for example. And then, but before I out, we are generating the VB here. Okay, so we are forcing the current into the transistor and generate to generate the VBE. So if your transistor is not diode connected, as in this case, it is diode connected, but for example, we'll use the circuit as we are going to see. For example, here, this circuit also, we don't use the diode connected BJTs. So you want to maintain the operating point such that this transistor will always be operating in the linear region mode. Linear region means here is the IV characteristics, IC versus VCE, and you want to make sure the voltage at the collector of this transistor is greater than the VBE, that is the forward voltage junction drop, so that the transistor does not saturate, which is this region. You don't want in this shaded area because this is saturation region of the BJT. You want it to operate in the linear region so that the current will be constant throughout it. And so the condition for that is this. So with that knowledge, it will generate the VBE, forward voltage drop, and it will have a temperature dependence, as we've discussed many times in earlier videos. So here is your generated voltage, here is your temperature in degrees centigrade, and here is the TCF of this curve, this voltage, which is approximately minus 0.3% per degree centigrade. So that's how we define it. Or in other words, you call it as a minus 2 millivolt variation per degree centigrade. Okay, so this has a strong negative TCF, this voltage. So idea is to generate another voltage which has a positive TC and then sum them together. Okay, so before we move that step, we have a look at the collector current and the input voltage relationship in the BJT. This is the collector current IC that is given by IS, which is the scale current, or usually it's in the range of nanoampere, pretty small. And it is reverse saturation current through a PN junction, and then exponentially Q times VBE divided by VT. Okay, and VT is your thermal voltage given by KT over Q. So at room temperature, you have the value of 25 millivolts at temperature T equal to 25 degrees centigrade, okay, at room temperature. So if this term is very, very greater than 1, then the equation sums up to or approximates to IS multiplied by this factor. So you see now there is a relationship between your current IC and the VBE of the transistor. Okay. Now, as I said, we have the strong negative TC of the generated VBE. So idea here is to generate another voltage which will have positive TC and then sum them together. So what you do here, you have this voltage source, and then you basically use these current sources to force the currents into the collector of these transistor. So let's say the collector current in this transistor is 1 ampere, and the second transistor with multiple emitters shown here has a larger emitter area, A equal to emitter area here. So the emitter area of this transistor Q2 is 8 times larger than the emitter area of transistor Q1. The effect of that would be it has a larger current capacity, that is IC2 will be 8 ampere, 8 times, and the current ratio, let's say IC2 divided by IC1 will be 8. Okay, or you can say that 1:8 ratio you select, where IC1 is 1 and IC2 is 8 times the IC1. And the effect is that you have this forward voltage drop across transistor Q1 and Q2 to be same. Okay, you have this one. And then there are some relationships. So here we define the current ratio, that is IC1 over IC2. It can also be linked to the voltage difference between the two transistors, that is Vbe1 minus Vbe2. So how do you produce this voltage difference, right? So what you do here, you put a resistor from the emitter of the transistor Q2 to the ground, so that you basically have this kind of circuit. So you have this transistor Q1, and then you have this transistor Q2, and the currents are coming like here, right here. And what you do here, you just have these resistor right here, R, and this is your ground terminal. So what you have here, you have VBE1, and then you have plus minus VBE2. And because of the different current densities in the transistors, you don't have the same current in the transistors, because we use the different resistors, the emitter areas, right? So therefore, the voltage drop across the R is given as I times R here, or let's call it RE. RE will be VBE1 minus VBE2. Okay, so because of the larger current in transistor Q2, you will have a smaller VBE across its forward bias junction. Okay, and that's how you take the advantage of this circuit, and you modify this circuit into this version. Rest remains the same. Okay, and that generated voltage difference, which is delta VBE, is theoretically given as KT over Q, natural logarithm of the two ratio of the two collector currents of the transistor IC1 and IC2. Okay, so here we see that different emitter areas result in the controlled current ratio. And the most important, that delta VBE that you have generated is another type of voltage. It has a positive TCF. It has a positive TCF. So what you have here, this is TC of this curve, and this will be positive. Okay, now you manage to generate a VBE which has negative TCF right here, and you manage to generate delta VBE which has positive TCF. Okay, but the VBE magnitude is approximately 0.7 volts. 0.7 volts right here, and the delta VBE must be approximately 0.5 volt, for example. Then only after summing this, the VBE plus delta VBE would be your V reference. Okay, so delta VB is usually not on the order of 0.5 volts, right? So you need to multiply this quantity delta VB with some factor. So let's call it M, and then only you will be able to produce 1.2 volt. This will be your 0.7 approximately, plus this will be approximately 0.5 volt. Then you will be able to produce 1.2 volt of V reference. And if you manage to produce that 1.2 volt, it will have, let's say, V reference. This is your temperature. And we say that it will have nearly constant behavior with respect to temperature, because on the first order, you cancel the negative TC of VBE with the positive TC of delta VBE. So that's the whole idea of band gap reference. So now let's dwell into our circuit simulators where we have used the components together, and we'll show you how we can actually design that circuit. Okay, so what I'm going to do here, so as you can see right here, we have this circuit ready here. Let me get rid of the drawing, and the name of the circuit is basic bandgap reference, as you can see here. So I have picked up the components from the library, which is right over here. Let me show you that. So here is my component library. I picked up that, and I just picked up components such as Q1, which you can see that I have this diode connected transistor, and then this is always going to be operating in the linear mode, that is the region right to this line here, so providing the constant current. And then I am using the transistor Q2 here, and I have the resistor in the emitter with respect to ground here, so you can see that, right? And then from the collector, I'm using another resistor R2. Here is the resistor R1. And then, as I said, we want V reference to be will be the sum of VBE plus the ratio of two resistor R2 by R3 multiplied by delta VBE. Okay, so this is a multiplication factor that will make delta VB approximately equal to VBE, and therefore V reference should be approximately equal to 1.2 volts, which is equal to the band gap of silicon. And that's why the name comes. So I'm using, like, let's say 10 volt supply here. Then I'm using this V plus that is connected right here, and I'm forcing 1 milliampere current into the circuit. That current is flowing here, that is coming right here, and then this current gets splitted into IB of 2. Then this current comes as a collector current of transistor Q1, and this current also goes as IB of transistor 1. And here I see there is IB, I see there is IC2, and this current is IR2 actually. This current is IR1, and then this current is IB3, and here I have IE3 right here. Okay, so the first voltage that I'm producing, I'm forcing this current into this transistor, and because of that I get this VBE drop generated, which is approximately 0.7 volt, let's say. Now this voltage is same and coming right here because collector and base pins of Q1 are shorted, right? And now I have another voltage drop here, which is VBE2. Let's call it VBE1. And then finally, there is this drop due to I3 multiplied by R3. That is my voltage right here. Let's call it as VE. So my VE would be VBE1 minus VBE2. So here I haven't used the because I have used the same transistor Q1 and Q2, I don't have an option here to select the emitter area of the transistor Q2 so that current densities, collector current densities or collector currents both in Q1 and Q2 can be different. So in order to do so, what I'm doing, I'm using R1 as 600 ohm, and here to the collector of transistor Q2, I am using 10 times the value of R1. So my current in transistor Q2 will be 10 times smaller than the collector current of transistor Q1. So I write here IC2 will be less than or equal to, rather I would say equal to IC1 divided by 10. So that's how by a factor of 10, my current in transistor Q2 got reduced. And neglecting the base current IB2 and IB1, I would say the same current is flowing through the resistor R3. Okay. And so yeah, so that's how I get this one. So let us find that out, how much is the voltages and all that. So if I say I have like 0.7 volt here, right here, and then I'm forcing this current right here in this one. So let us do that now. Now what is happening here? I have this resistor R2 and the voltage drop across this will be IR2 into R2. Okay, this is the voltage I'm interested in. So let me write here, that is VR2 would be IR2 times R2, and IR2 is my IE2 times R2, and IE2 is my VE divided by R3 into R2, which is equal to VBE1 minus VBE2. Remember, VE is the difference between this, and this is R3, and this is R2. So I would say my voltage across the resistor R2 would be R2 over R3 into delta VBE. So that's the voltage I'm producing here, okay, which is basically the voltage right here. Okay, therefore the voltage here of which is VBE3 of the transistor Q3. Therefore, I would write V reference is equal to this voltage VB3 plus this voltage, and that's how the voltage VCE of the transistor Q3 is, right? And that's how we get here. You can write here VBE plus R2 over R3 multiplied by delta VB, and that should be approximately 1.2 volt. Okay, so now let us understand by doing some analysis. So we are all set to run our analysis right here. So before that, I would like to highlight, I have labeled the net. This net is labeled as VB, which is the voltage drop across the transistor Q1. And I have labeled this net to be VE, which is the voltage drop across the RE. Then I have labeled this net to be VB3. VB3 is essentially my VB3 right here. So with that simple arrangement, let me actually simulate my circuit, and I would just click right here. Before that, let me get rid of the drawing, or maybe just keep it for a moment. Click simulate. I have got this white table about all the voltages and the currents into the circuit. So let's have a look. Let's clean the drawing right here and now have a look here. you have this voltage at the VB, which is this net. This is 0.7 volt, 0.76. So it is forward biasing the PN junction, making that transistor of providing a constant current in a linear or active mode. Then VB3 is again 0.7 volt. That is your transistor biased for this PN junction. VE is your 0.056. So remember, that's the voltage you drop across the resistor R3, and which is the difference between this VB minus this two nets. That is VB minus VE. So look at this, VB is 0.76 and V is 0.05 is your VBE2, and obviously VE will be smaller because there'll be a slight difference between VB1 and VB2, and that difference is being dropped here. And this voltage that is dropped across the R3, which is VE, has a positive TCF, but the magnitude is pretty small. That's why we need to multiply this with some factor. And in the theory we just saw, we take the ratio of R2 over R3. That's the voltage that is generated here, right here. Okay. And look at this final output. V reference is 1.26, exactly what we want. That is our band gap reference. Now with the supply volt of 10 volt, and then you have collector current of transistor Q1 to be about 0.8 milliampere. Now this 1 milliampere is being split into all three branches, 1, 2, and 3. So collector current of transistor is 0.8 milliampere. Then the collector current of transistor Q2 is obviously 10 times smaller, which is 93 microampere. So remember, this is 93 microampere and this is about 820 micro. So it's about more or less 9 to 10 times larger. Then you have collector current of transistor 3, which is pretty small, is about 72 microampere. Okay, so your 1000 microampere current is being divided into three parts. The major current is being taken up by this transistor Q1, which is about 824 microamperes. And then you have the base currents, and then you have the emitter currents of all these transistors, and the resistor currents are also shown. So once that is done, what if I want to reduce the supply voltage? Because I said bandgap references are used for a supply voltages smaller, because the technology is shrinking and the circuits are being designed to operate at a smaller voltages. So let's rerun the analysis. And now you see we still have the reference voltage of 1.2 volt, which is required one. The VB is 0.76, VB3 is 0.7, and the voltage VE is 0.05, and this voltage has positive TCF. And VB3 is 0.7. This voltage has negative TCF, and we are summing them too with this factor multiplication R2 divided by R3, 6 times larger than the VE, will give me final output of 1.26 volt. Look at the collector current now is still the same. That is because this is I'm forcing a constant current here. What if I want to change the collector current? Let's say I am using 0.5 milliampere, 500 microampere current. And with that said, I am now getting the value less than what is required here. Okay, so you have to make sure that your bandgap reference is 1.2. This is what, and you need sufficient current to be injected into the circuit. So let's go back to 1 milliampere again and simulate this circuit. And here you are, right? Now, with that done, we can now run the temperature analysis to see how the reference behaves. And we'll also plot the individual voltages like VB1 and then VE, which is the delta VBE. Okay, so let's do that. We need to recall the syntax for the temperature sweep. So let me write that command right here. What I'm going to do is I will come here at the top of the menu and click the spice directive, and then I will say dot step temp, and then I will say list, and then I will write these parameters. So let's say 25, then 50, then let's say 70, and then 100, and whatever the values I want. And then this is my command right here. If I right click here, it gives me this step parameter editor, statement editor, where I'm using the name of the parameter to sweep is global temperature. I'm using the step command to overlay simulation results while sweeping user defined parameter. Nature of the sweep. So instead of list, let's say linear, and the start value, let's change it to -40, for example, and let's stop value, let's say 120, and increment, let's say 5, something like that. So it is going to step from -40, start with that and end at 120 degrees centigrade at the step of 5-degree increment from -40 onwards. So with all them, let's click run. And first, I want to see the negative temperature coefficient of this transistor delta Vbe. So look at this schematic. I am prompted to click to plot the voltage at Vb. So I'll click here and look at this behavior, which is my junction voltage is having a negative behavior with this temperature. As the temperature increases, this voltage is dropped, and the slope of this tells me this has a TC of a minus 0.3 percentage per degree centigrade approximately, or I can say it has a value of -2 millivolt per degree centigrade. So for every degree centigrade rise in temperature, my voltage drops, which is the VBE of transistor 1. Okay, now on the same, I would like to plot the difference between VB1 and VB2. So what I'm going to do here is simple. I will come back to schematic and I want to plot delta VBE, which is VE. I will see here and look at this now. The blue curve, it has little bit improved version here. Like if I choose to add plot pane and then VB goes up, and look at this now, VE. This voltage has positive TCF. It is rising from 44 millivolt initially up to 70 millivolt. The very good results we are getting. So both these curves can be added together to generate the reference. But as I said, look at the magnitude of this VE, which is 44 millivolt, or approximately at room temperature is 50 millivolt. Now, adding 50 millivolt to the 800 millivolt gives me about 850 millivolt output. But my band gap voltage requirement is 1.12, because at that voltage only, I am having nearly 0 TCF. Okay. Other than that value, I will have a larger TCF relatively. So what I have done, I have actually taken the ratio of resistors R2 divided by R3, because the current through the R2 multiplied by the value of R2 is the voltage drop across R2, which is this current IE. As neglecting the base current of transistor Q2, I'm going to have the emitter current right here is equal to the collector current right here. And the voltage drop across R2 is that current multiplied by R2. So we have seen that. So R2 divided by R3. So it will be like about 100 times or 10 times. So my VE will be multiplied by 10 times, and that's why I will get this value. So what I'm doing here, I will now plot the V reference, and let's do that. So I will add plot pane, and maybe let me clean this drawing here. Okay, and go back here and look at this. Now, well, this is still dropping here, but we say that at room temperature, for example, here, the value of the band gap is 1.12, and the slope is, if you take the, if you calculate the change in voltage divided by change in temperature, you will have a smaller, much smaller TCF than the individual TCF of the green and the blue curve. And that's how you actually do that. Let's put it right here. Okay, so here you have this reference value. Okay. So I think we covered that, how to generate the band gap reference. Still, it has some value. Look at the value for such a wide range from -40 to 120. Your reference is varying from 1.3 to 1.16. So you can just apply some formulae and the calculations to see the percentage changes. So I think still you have the reason. There is a reasonable tolerance level here, 1.16 to 1.3, and average is about 1.23, or even, yeah, 1.2. So hope you understood this video about how we can generate the basic band gap reference voltage, which is relatively independent of the temperature. We'll see some modifications of those circuits also. And wish you happy learning. If you like this video, click like, share with others, put some comments, and stay tuned for more technically rich contents like this. Till then, wish you happy learning.